In this video, I want to look at u-substitutions and integrals that go back to inverse trig functions. So I want to start with a very brief review of the derivatives and corresponding antiderivative formulas involving the inverse trig functions. The first one that I expect you to know is that the derivative of the arctangent function is known to be 1 over 1 plus x squared. The corresponding antiderivative formula, of course, is that the integral of 1 over 1 plus x squared dx is going to be arctangent of x plus whatever c that you want to add. The only other inverse trig function that we will worry about in this particular calculus class is the inverse sine function. And in Calculus 1, you should have seen that the derivative of the arcsine function is 1 over the square root of 1 minus x squared. So the corresponding antiderivative formula is that the indefinite integral of 1 over the square root of 1 minus x squared will be the arcsine of x plus any constant that you want to add. What I want to look at now are how u-substitutions get involved in integrals that are going to go back to either the arctangent or the arcsine. So let's look at our first example. Our first example is going to be this. I want to find the integral of 1 over the square root of 1 minus 4x squared dx. Now, it's tempting to think about u being equal to this whole mess here, but when you do that, the u substitution is not going to work. It's going to fall apart. The trick in this one is to realize that 4x squared is the same thing as 2x quantity squared. And when I do that, I can rewrite this integral as the integral of 1 over the square root of 1 minus, and I want to emphasize what I'm doing here. So in new color, I'm going to put that. And the square root goes all the way over to that. And then we have a dx. And now at this point, I realize that I've got something that looks kind of like the derivative of arcsine, except that I have a 2x here instead of an x underneath that squaring. So I'm going to now do the following substitution. I am going to let u be equal to 2x. du then is 2 times dx. I will patch my integral up by doing a 2 over 2. Let me write more carefully. And this 2 and the dx go together to form the du, and using this substitution, my integral becomes 1/2 the integral of 1 over the square root of 1 minus u squared du. And this integral here is known to go back to the arcsine of u. So my answer is going to be 1/2 times the arcsine of u plus any constant that I want to add, and u, of course, was 2x, so the final answer will be 1/2 times the arcsine. Let me write that better. The arcsine of 2x plus any constant that I want to add. Well, let's look at another example. Our second example is going to be a little bit more subtle looking. We're going to have the antiderivative of e to the x over 1 plus e to the 2x dx. And this kind of thing often confuses students, and they're not quite sure about what to do because there's an e to the x here and there's an e to the 2x here. And if you try to make u equal to e to the x, you might initially get confused because of the notation. So what I'm going to do is I want to remind you of an important fact. It turns out that something like e to the 2x by exponent rules is going to be e to the x quantity squared. And that's going to be the critical thing for rewriting this integral in a fashion that lets me figure out what to do with the integral. So I use this fact, and I get that the integral becomes e to the x over 1 plus, and I want to highlight the new stuff. I'm changing that e to the 2x into e to the x quantity squared. And then, of course, I have the dx. And once I look at it like this, I realize that I have a composition, and if I think about making u equal to e to the x, this is going to go away into the du, and I should get something that's going to go back to the arctangent. So we're going to make this substitution. I'm going to let u be e to the x. Du is going to be e to the x dx. This e to the x and that dx go together to form the du. And when I rewrite the integral, I am going to have 1 over 1 plus u squared du. And that's known to go back to arctangent of u plus any constant that I want to add. And so my final answer will be arctangent of e to the x plus whatever constant I want to add. Well, let's look at another example. So in this example, I want to find the antiderivative of x over 1 plus x to the 4th dx. Now the temptation here is to be thinking about letting u be something like maybe either x to the 4th, and then du is 4 times du would be 4 times x cubed, and I don't have an x cubed in this integral, so that's not going to work. Likewise, if I let u be the whole denominator, du is still going to be 4x cubed, and I don't have an x cubed, so that's not going to work. The trick here is to realize that x to the 4th is nothing more than x squared squared. And if I use this fact, I can rewrite my integral as the integral of x over 1 plus x squared squared, and then I have, of course, the dx. Now I'm going to write my substitution over here since I'm out of room over here. At this point, I realize I've got a composition. The inside function is an x squared. That x is part of the derivative of that x squared's derivative, and so it is reasonable to try this for my substitution. I am going to let u be x squared. Du is 2x dx. I will need to patch the integral up by multiplying by 2 over 2. That 2, the x and the dx all go together to form the du. So when I use this substitution, I get the integral becoming 1/2 the integral of 1 over 1 plus u squared du, and that's going to go back to 1/2 times the arctangent of u plus any constant. Of course, u was nothing more than x squared here. I want to do one last example, which is a variation on the same thing. So this time, what I want to do is I want to look at the antiderivative of x squared over the square root of 1 minus x to the 6th. Oops, I've got the wrong thing. I want this to be an x. No, that's what I want. X squared over the square root of 1 minus x to the 6th dx. Now, again, if I try and make u equal to x to the 6th or 1 minus x to the 6th, I don't have an x to the 5th inside the integral. So those u substitutions that immediately come to mind are not necessarily going to work. But I want to recall a basic algebra fact. X to the 6th is x cubed squared. And because of that, I can think about rewriting this integral, first of all, as x squared over the square root of 1 minus x cubed squared dx. And with that highlighting, I see that I've got something that kind of looks like a derivative of an arc sine. And if I make u equal to x cubed, this x squared should go into the du. So at this point, I want to let u be equal to x cubed. Du is 3x squared dx. I will have to fix my integral up by multiplying it by 3 over 3. That top 3 comes in, gets married to that x squared and the dx, and these form a du. And so with this substitution, my integral becomes 1 over 3 times the indefinite integral of 1 over the square root of 1 minus u squared du, and that's going to go back to the arc sine of u plus a constant. And so my final answer becomes 1/3 times the arc sine of my u, which was x cubed, plus any constant that I want to add.